Okay, so what we're going to look at next are some properties of a locus. And what these hopefully will do, these are some general properties that, well, so we don't have to do the calculations each time, right? So this will allow us to quickly sketch over a locus so we have a good idea how the closed loop poles are going to change. So to give you an understanding, we'll look at another example. But we're going to start, right, with k times s plus 1 over s plus 2. And so this is k g of s, c of s, and we're going to put in the feedback path, this is h of s, we're going to put s plus 3 over s plus 4. Okay, so now for our open loop transfer function, what we're going to do is basically we'll start here and end here. All right, so we'll basically open the loop so we don't have any. And so when people talk about the open loop transfer function, typically they're going to look at this k g of s times h of s. So basically starting here, I can't even see it here, starting here, right, following the loop until we get to there, right? So we have kg of s, h of s, and that would be simply k times s plus 1 times s plus 3, well, s plus 2, s plus 4 in the denominator, right? So k g of s, h of s. All right, our closed loop transfer function, we have, well, that's going to be k g of s over 1 plus k g of s h of s. So this is k times s plus 1 over s plus 2 over 1 plus k times s plus 1 times s plus 2 times s plus 3 divided by s plus 4. So we can simplify that, right? And then we end up with k times s plus 1 times s plus 4 times s plus 2 times s plus 4 plus k times s plus 1 times s plus 3. And the goal here is to compare the open loop transfer function poles and zeros to the closed loop transfer function poles and zeros. Okay, so start with our open loop transfer function zeros. All right, here's our open loop transfer function. We have two zeros, right? In the numerator, we have -1 and -3. And so the open loop transfer function zeros are simply the zeros of g of s and h of s. And our open loop transfer function poles are, again, same equation, -2 and -4. And these are the poles of g of s and h of s. Now, what I want you guys to figure out, so group exercise, right? And get on FaceTime and talk to you, or Zoom and have a Zoom breakout meeting. All right, or you can do it yourself. But either way, I want you guys to find the closed loop transfer function zeros. And the closed loop transfer function poles. And we're gonna, for the poles, I want you to look at two different cases. For k equals 0 and k is equal to infinity. Okay, so, all right, so if you want to pause right now, and then we'll compare answers. Okay, so closed loop transfer function. Remember, now we're working with, here's the closed loop transfer function. So the zeros, well, are -1 and -4. Well, where did those come from? Well, here is, let's come back up here, right? We got -1 from here and -4 from here, right? So these are the closed loop transfer function zeros are simply the zeros of g of s and the poles of h of s. Okay, now to calculate the closed loop transfer function poles, right, we're going to use the denominator here, right? So we have, let's just write that down, right? So we have s plus 2 times s plus 4 plus k times s plus 1 times s plus 3. Okay, so then for k equals 0, well, when k is equal to 0, we can ignore this part, right? Because k is equal to 0. And we end up with -2 and -4. All right, and again, that's not, this is the poles of the open loop system. So this would be the poles of k of k, g of s, h of s, right? When k is equal to infinity, though, well, when k is equal to infinity, we can, this term right here, darn it. Now we really messed it up. There we go. This term here, when k goes to infinity, this term here now is going to dominate, right? Because k goes to infinity, doesn't really matter what s plus 2 and s plus 4 are. So our poles now are at -1 and -3. And those were simply the zeros of k, g of s, h of s. So those are the zeros of the open loop system. Okay, so let's see if we can sketch all this. So if we do our root locus, imaginary, real, we have pole with -1, -2, -3, and -4. Okay, we said we were going to put for our open loop transfer function poles, which are -2 and -4, we're going to use x's, -2 and -4. And our open loop transfer function zeros, we're going to use an O for 0, so that's -1 and -3. And then our closed loop transfer function poles, well, when k is equal to 0, right? When k is equal to 0, they're at -2 and -4. They're at the open loop transfer function poles. So k is equal, this is k is equal to 0. And then when k goes to infinity, right now they're at the open loop transfer function 0. So they moved over here. So this is at k is equal to infinity. Right, so we've moved from the open loop transfer function poles to the open loop transfer function zeros, okay? And that is, obviously works for this particular example, but that is that's a general example. Oh, and then we'll use so we're using closed loop transfer function poles, we're using here. The closed loop transfer function zeros, we don't necessarily find those that often, but if we do, right, I mean, they do have an impact on the response. We'll use a square, right? And those were at -1 and -4. Hopefully you have all the wonderful colors so that you can keep track of all that. Okay, so we're going to call a pause here, and then we're going to look at nothing more than the vector representation that messed this up earlier, but hopefully it'll make more sense now. It's really critical now, so hopefully it'll make much more sense. So, 1, 2.